Dear students, today we'll see what do we mean by filters, and in that we will see what is a low pass filter, and this filter combination we will see in passive networks. So let's start with today's topic. So today's topic is low pass filter, and in this session we are going to see the following contents: what is a filter, terms related to filters like pass band, stop band, cutoff frequency, characteristics curves, that is ideal curves of low pass filter, high pass filter, band pass filter, and band reject filter. Then low pass filter and its concept, how does low pass filtering take place? Types of low pass filter, or T type and pi type. Then frequency response of low pass filter, applications of low pass filter, and an experiment on low pass filter. So let's start first with what is a filter. Filter which are used in our communication. So here we can see the definition of filter. A filter is a circuit which is capable of passing certain frequencies while attenuating or rejecting other frequencies. Now what does this mean? This is a network, this is a circuit that produces frequency dependent change in the response to the signal being processed, and it is considered as a filter. It is a frequency selective circuit that is designed to pass frequencies, to pass the signal with frequencies within a specific range and reject signal with all other frequencies that fall outside this range. So it is a frequency selective network. Okay. So now in this we'll be having types like low pass filter, high pass filter, band pass filter, and band rejection filter. Okay. So let's start with filter or concept now. So here there are few terms which are related with filters. Number one is, what is pass band? Now whenever we use a filter, it is going to pass signals of certain frequencies. Now the range of frequencies that a filter will allow to pass, the signals which are allowed to pass in a particular range of frequency, that range of frequency which will be passed by the filter is termed as pass band. So if you see the definition, the range of frequencies that a filter will allow to pass is termed as filter's passband. And ideally, if you speak, in that passband, there will be no loss. The loss will be zero. Okay. So the loss will be zero, and therefore all the signals of that frequency range are passed by that filter. Okay. So it is the passband of the filter. Then we'll go to see what is stop band. The range of frequencies that a filter will attenuate or stop or reject is termed as filter stop band. So all the signals in that particular range which the filter will going to attenuate or reject or stop is called as stop band. So the frequency range of those signals which are stopped by the filter is called as stop band. So the range of frequencies that a filter will attenuate or stop or reject is termed as filter stop band. An ideal filter will have infinite loss in its stop band. So there will be no gain at all. It will be complete loss. The output has to be zero ideally. Okay, so it is infinite loss in the stop band. So the filter will not process signals of those frequency range which fall in the stop band. Then we'll go to see what do we mean by a cutoff frequency. Now a cutoff frequency is a decidable frequency, a frequency which decides where the pass band should start or pass band should end, or stop band should start or stop band should end. Now this frequency is defined as, it is the frequency at which the output of the filter drops by 3 decibels from that of the pass band. Now in a pass band, it will be having the maximum gain. Now from that maximum gain, if you come down 3 decibels at that range, at that point of the magnitude of the output, whatever frequency you get, that frequency is the cutoff frequency. So it is the frequency at which the output of the filter drops by 3 decibels. Now say for example, if you are having a frequency response, this is frequency response, this is your gain. Now gain is given in decibels and frequency is given in hertz. And then if you start here, now here, say for example, we are going to pass frequencies up to certain range. Say the gain will be high for all those signals up to certain range. And say here at this range, after that you are going to stop. So once you stop it, it comes, the graph comes like this. So in this case, this is the maximum gain. This is the maximum gain. And from here, if you come down 3 decibels, come down 3 decibels, 3 decibels. So here you will get a point. The point, at that point, whatever frequency you are going to get, that is the cutoff frequency. Okay. So this is the cutoff frequency. So whenever you have the graph where you are going to decide the stop band and pass band, so you have to come from the maximum gain and come down minus 3 decibels, and then the frequency at that gain will be your cutoff frequency. Okay. Now this cutoff frequency is also called as minus 3 decibel frequency. It is also called as break frequency, or it is also called as corner frequency. Okay. So these are the related terms with filters. Then we will go to see a classification of filters. Now here we have shown the graphs of filters by which you can classify, that is you are going to classify filters on the basis of pass band. Now on the basis of pass band, if you are going to classify filters, then we will have 4 types of filters. One is low pass filter, high pass filter, band pass filter, and band reject filter, which is called as notch. Now these filters are nothing but, in low pass filter, all the frequencies, all the signals of frequencies below the cutoff frequency will be passed, as shown here. Here you are going to pass all the frequencies below. Okay, so here this is the cutoff frequency. So below that, all the frequencies, all the signals of those frequencies will be passed, and above that the frequencies will be stopped. So it is a low pass filter. Similarly, if you see high pass filter, then you can refer this ideal graph. Now here you can see this is the cutoff frequency. All the frequencies above cutoff frequency are passed, and all the frequencies below cutoff frequency are stopped. So it is high pass. It is going to pass filters above cutoff frequency. It is going to pass frequencies above cutoff frequency. Okay. Then we'll come to band pass filter, the third one. So in band pass, you will be having 2 reference frequencies. One is say F1 and F2, which will be the 2 cutoff frequencies. So all the signals which fall into this frequency range, that is from F1 to F2, will be passed. This is pass band, and below that, below F1, it will be stop band, and above F2 it will be stop band. So here it is going to stop all the frequencies, whereas it is going to pass the frequencies between F1 and F2. Similarly, if you come to band reject filter, then it is going to reject the band of frequencies which are within particular range of F1 and F2. So here again you can see the first cutoff frequency, second cutoff frequency. So here this range you are going to stop. This is stop band, and below F1 you are going to pass. This is pass band, and above F2 you are going to pass. This is pass band. Okay. So in this way you are going to have the 4 types of filters which are based on the pass bands. Then again here the actual ideal graphs or ideal curves are shown. So here you can see the ideal curves. So here the first one is shown as the low pass filter. So in this low pass filter you can see that the frequencies below the cutoff frequency here. So here is the cutoff frequency. Frequencies below the cutoff frequency are passed. So this range you can see it is for the pass, and the frequencies above cutoff are stopped. So this is stopped. Okay. Similarly, if you see high pass filter, all the frequencies till the cutoff frequency are rejected or stopped, and the frequencies above the cutoff frequency are passed. Similarly, if you see band pass filter, then there are two references of frequencies. There are two cutoff frequencies. This is one cutoff frequency and this is other cutoff frequency. So all the frequencies between those two frequencies will be passed, and frequencies above that and below that, below this band and above this band will be stopped. So this here you can see stop band, and here you can see stop band. Okay. Similarly, if you go for band stop filter, which is also called as band reject filter or band elimination filter, you will be again having two cutoff frequencies. So all the frequencies within that range will be stopped, and the frequencies below that range will be passed. So here you can see pass band, and the frequencies above the largest or cutoff frequency will be again pass. So here again you can see pass band. Okay. So in this way you can have band stop filter. Now if you see this classification summary, then based on frequency selection there were four types of electronic filter which we have named as low pass filter, high pass filter, band pass filter and band reject filter. Okay. Then we'll come to specifically to know what is low pass filter. As we have seen, it will be a filter which will pass frequencies starting from 0 up to a designated frequency which is called as cutoff frequency. Okay. Now here if you see the definition for it, the filter circuit which allows passing of the signals having the low frequencies starting from 0 to a predetermined cutoff frequency and rejects the signal having the frequency beyond that cutoff frequency is called as low pass filter. That means if you see the curve or the graph or the frequency response, if you see the ideal frequency response of low pass filter, then you can show it in this way. So here you can see this is your x-axis is frequency and y-axis is gain, and say this is 0 point. Then from 0 to some designated or predetermined frequency which is called as cutoff frequency, all the signals below that frequency will be passed. So they will be having gain. Okay, so this will be pass band, and all the frequencies above the cutoff will be stopped. This will be stop band. Clear? Now this is because it is going to pass the frequencies below cutoff frequency, that is from 0 to the cutoff frequency it is going to pass, and because it is going to stop the higher frequencies, and because it is passing the lower frequency, it is called as low pass filter. So here the name comes with reference with the pass band. So if you see, it is going to pass the frequencies below the cutoff frequency, that is from 0 to FC. So it is low frequencies what it is going to pass. So it is called as low pass filter. Then if you take an example of it, say for example a 50 megahertz signal is present. There is a signal whose frequency is 50 megahertz, but we need the signal up to 25 megahertz only. Then in that case we don't want that extra 25 megahertz. So in this case we need a low pass filter which will allow the passing of the signal having the frequency from 0 to 25 megahertz, and it will reject the signal having the frequency above 25 megahertz. So we can select the frequency up to 25 megahertz and pass. So 0 to or 25 megahertz will pass, and all the frequencies above or 25 megahertz will be stopped. So it will be a low pass filtering example. Okay. Then we'll come to see what are LC filters. That is, LC filters means which will have inductor and capacitor. So it is a combination of inductor and a capacitor. We can also have RC filter. We can have resistance and our capacitance, and we can also have LC filter. Now in this session we are going to see LC filter, in which we are going to use inductor and capacitor. So LC filters refer to circuits consisting of a combination of inductors L and a capacitor C to cut or pass specific frequency bands of an electric signal. Now we all know that our capacitors can block DC but pass AC. That is, it is going to block direct current and it is going to pass alternative current. Conversely, inductors will pass direct current and they will block alternating current. This is because of the reactance provided by those components. So reactance provided by capacitance. So XC will be equal to 1 by 2 pi FC. Okay, so here you can see frequency is inversely proportional to the opposition to the flow of current. So it is going to pass all the high frequency, because at high frequency the opposition to the flow of current will be less. So it is going to pass AC, it is going to pass all the high frequency, and it is going to block DC. Similarly, if you see the reactance of inductor, it will be XL is equal to 2 pi FL. So here reactance is directly proportional to F. So that means if the frequency is high, reactance is more, it is going to block AC. So it is going to block AC, and if the frequency is less, the reactance is less, it is going to pass DC. It is going to pass DC because DC will be of lower frequency. Okay. So in this way, these components, that is inductors and capacitors, can be connected in series and parallel to decide a frequency range by the circuit which can be passed or which can be blocked, and hence these components are used to build up filters. Then we'll come to the concept of filters, low pass filter. Now here in low pass filter, we always see that the LC component, in LC are components, the component which will be passing low frequencies and blocking high frequencies will be connected in series. So here you can see the component which can do that is inductor. Now inductor is one which is going to pass low frequencies and it is going to block high frequency. So here you can see we are connecting inductor in series because we know that is the opposition to the flow of current given by the inductor, that is XL is equal to 2 pi FL. So if the frequency is less, opposition to the flow of current is less, and therefore it will pass those frequencies. So lower frequencies will be passed. Okay. Similarly, for low pass filter action, we are going to connect capacitance in parallel because the capacitance reactance is given as Xc is equal to 1 upon 2 pi Fc. So it is going to pass AC and block DC. So low frequencies will be blocked and only high frequencies will be passed and they will go to the ground. That means the combination of L and C will see that low frequencies will go ahead to the load and high frequencies will go to the ground. That means it is going to pass all the frequencies below a specific frequency and it is going to stop all the frequencies above a specific frequency. So if you see the graph for it, so here you can see the graph of gain versus frequency. So here you can see all the frequencies below a cutoff frequency are having high gain, and then approximately here you will be having your cutoff frequency. After that you can stop all the frequency. This is stop band, this is pass band. Okay. So in this way, for low pass filtering, the inductive component, the inductors should be connected in series of the circuit and a capacitor should be connected in parallel of the circuit. So it will give the concept of low pass filters. Then here you can again see the frequency response for low pass filter. As we have told earlier, low pass filter is going to pass all the frequencies below the cutoff frequency, and it is going to stop all the frequencies above the cutoff frequency. This is the ideal graph. This is the ideal graph. So here we can show a sharp breakdown at the cutoff frequency. Similarly, if you see a practical response, then there is a falling of the gain over here, and this fall off you can take till -3 decibels here, and you can mark the cutoff frequency. So all the frequencies above that cutoff frequency will be passed. This is pass band, and all the frequencies below the cutoff frequency will be stopped. So this is stop band. Okay, so the first graph is ideal graph, and the second graph is a practical graph. So here if you see the types of low pass filter, so here we can see the first type, which is called as T type. This is a T type low pass filter. Now here again we are going to use inductor components in series and a capacitor component in parallel. Now here inductor component in series and a capacitance in parallel, but we want a shape which looks like letter T. So here we want a shape which looks like letter T. So here you can see this is a shape of letter T. Now because of this, it is called as T-type filter, and the component which we are going to put in series, that is L, will be divided into two parts, L by 2, L by 2 here. So two halves, and then the capacitor component is in parallel. Now this combination is going to do low pass filtering, and this is called as T-type low pass filter because you have a T-type structure of alphabet T. Then this T-type filter is used. Now if you want to use a low pass filter, and in that low pass filter, if there is a need in the application that the input impedance should be low and the output impedance should be low, then we can go for T-type filter. Similarly, if the need of the application is when the input impedance is high and output impedance is high, then we have to go to a low pass filter whose structure is pi type. That means for pi type filter, the input impedance is high and the output impedance is high, and the structure looks like this. So here you can see same, again we have the same concept, that is the inductive components are in series and capacitive components are in parallel. So here you can see this is the inductive component and this is the capacitive component over here. So here you can write it as C by 2, C by 2. Okay, now here this is also going to act as low pass filter, but the structure you see here, this is one leg, this is another leg, and this is your top part. So it looks like pi, the symbol pi, so it is called as pi type filter. So if you see the frequency response, as we have seen earlier also, below the cutoff frequency, so here you can see the cutoff frequency is here. Below the cutoff frequency, all the signals are passed. So this is your pass band, this is pass band, and above the cutoff frequency, all the signals are stopped. So this is your stop band. Okay, and in this pass band, till -3 decibels, if you take the point, so you can mark your cutoff frequency here, and that will be the bandwidth of your low pass filter. That will be the useful range of your low pass filter. So here you can see bandwidth of low pass filter. Then we'll go to see applications of low pass filter. Low pass filters can be used in many applications. To name a few, we can have low pass filter is used in digital signal processing. It is used in audio equalization purpose. It is used to reduce high frequency noise in audio, and it is used in anti-aliasing filters in analog to digital converters. Okay, now as far as the experiments are concerned, we will see one experiment in our lab. So that experiment's aim will be to construct and test. So aim of the experiment will be to construct and test passive low pass filter. We are speaking it as passive because we are going to use all the passive components like inductor and capacitor. Passive low pass filter, and here we want a T type T-type passive low pass filter, okay, for a given cutoff frequency, for a given cutoff frequency. So here we can have the circuit like this. We can have the circuit like this, the inductor here, then you can have a capacitor here, and again you can have a inductor here. Clear? Now this will be your low pass T-type filter. So here input you can give the function generator where amplitude will be fixed and frequency you are going to change. So here let's keep the amplitude of this input as 5 volt, and we will change the frequency from 100 hertz to 10 kilohertz. Okay, so here this is L by 2, this is L by 2, this is C, and here we will have a resistance which will be your output resistance R0, which will be taken as 600 ohms, and here you are going to see the output on CRO. Here you are going to see the output on CRO. Okay, now here to start with we should know what is the expression of a cutoff frequency for low pass filter. Now if you see the expression for a cutoff frequency for low pass filter, then the cutoff frequency is given as FC is equal to 1 by pi root LC. Okay, now this is the expression for cutoff frequency in a low pass filter. Now with this we can also have expression for the inductor. So inductor expression can be derived as L is equal to R0 upon pi FC, that is the cutoff frequency, and a capacitor can be given as C is equal to 1 upon pi R0 FC. Okay, now here these are the expressions of inductor and a capacitor. Now when you want to design a low pass filter, then we are having these expressions. Now with these expressions what we can do is we can find the component value. Now here if you go to see the design for low pass filter, then we can write the design like this. So here we will have design. Now in this design we know the expression for cutoff frequency. FC is equal to 1 upon pi root LC, 1 upon pi root LC. Okay, and we know that inductor L is equal to R0 upon pi FC, and C is equal to 1 upon pi FC R0. Okay, now here if we want a frequency which can have a cutoff frequency, if we want a circuit whose cutoff frequency is around 2 kilohertz, so let's take, we are going to design the low pass filter whose cutoff frequency is 2 kilohertz. That means it is going to pass all the signals whose frequencies are below 2 kilohertz, and it is going to stop all the signals whose frequencies are above 2 kilohertz. So if you take this FC is equal to 2 kilohertz, that is nothing but 2 into 10 to the power of 3 hertz, and we'll take R0 is equal to 600 ohms as we have seen in the circuit. Then we can find the value of L and C with the above expressions. So here you can find the value of L. L is equal to R0 upon pi FC. So here it will be nothing but 600 upon 3.14 into 2 into 10 to the power of 3, which will be nothing but L is equal to 95. So here you can see 95.49 millihenries, and because in our circuit we want L by 2, so L by 2 will be 47.75 millihertz. Similarly, you can also calculate capacitor C. C is equal to 1 upon pi Fc R naught, which is nothing but 1 upon 3.14 into 2 into 10 to the power of 3 into 600. This will be nothing but C is equal to 0.265 microfarad. Okay. Now here in this we are going to use these components and we are going to build up a circuit. Now that circuit will be looking like this, as we have seen earlier. Here you will be having L by 2, here we will be having C, and here you will be having L by 2. Okay, and then here you are going to connect the function generator whose frequency will vary, and here you will be having the R naught as 600 ohms. So here this will be the inductor, which is 47.75 millihenries, and here again same 47.75 millihenries. This capacitor will be 0.265 microfarad. Okay, this R naught will be 600 ohms, and this V in will keep the amplitude fixed at 5 volt and will change the frequency from 100 hertz to 10 kilohertz. Okay. Now here when we take the observation table, when we start the experiment, we are going to give the input of 100 hertz with a V in voltage of 5 volt. So here if you see the observation table, so we will take V in is equal to 5 volt, and in our observation table we'll have serial number of the observations like 1, 2, 3, 4, and then we'll have input frequency which we are going to change, input frequency in hertz. So this we are going to change as 100 hertz, 200 hertz, okay, till your last 10 kilohertz, because our cutoff frequency at 2 kilohertz, so we have to take suitable readings. Then we will note down the output voltage on CRO here, output voltage on CRO. So here you can connect your CRO, here you can connect your CRO and note down the output voltage. So output voltage for every change in frequency is going to be noted, and then you note down the gain in decibels, which is given as 20 log V out upon V in. So V out we are going to get here, this is V out readings, and V in is whatever we have kept constant in the beginning, that is 5 volt. So that ratio, log of that ratio multiplied by 20 will give you gain in decibels, and then you can see this gain. And when we plot the graph for the same, we will plot it like this. It will be frequency versus gain, and in that you can see that initially till the cutoff frequency the gain will be high, and at the cutoff frequency that gain will decrease. And here minus 3 dB you should get 2 kilohertz. So this will be 0. So all the frequencies below 2 kilohertz are passed, and the frequencies above 2 kilohertz are stopped. And if you show this, if you verify this, then you are verifying the working of a passive low pass filter in T-type combination. Okay. Thank you, students.